Thank you for coming to the August IJGIS webinar. And we have 4 outstanding researchers in GIS-related research on how to look at the human mobility with geo-tagged data in the urban area. As you can see on the screen, that we have Professor Ma, Professor Saraki, Professor Oki, and Professor Zhang across the Euro-Asian continent. And this is outstanding. And one thing that we really want to promote is international collaboration on GI science. So they are based on their paper published in IJGIS, and this paper, even though it just appeared last year, but have attracted a lot of attention and good views, citations, and autometric metrics, which means they have distributed across social media quite well. We will have Dr. Ma cover the first presentation to overview the research. Then have Dr. Saraki and Dr. Oki give a general discussion on the behavior at the large-scale earthquake. I think that after a major event, human mobility will have significant change, and they will give it to a novel thinking and method to analyze those mobility changes. And finally, we have Dr. Zhang. He is really into the theoretical account of urban morphology and the hierarchy of organization of cities and geographical phenomena. And he will give us a very novel thinking from a holistic view of urban system to recognize the beauty of urban development. A very interesting topic overall. So Dr. Ma, please take on to start your presentation.
Thanks, May, for your kind invitation. And also thank you everyone for coming. It's a super honor and pleasure for me to present in this IJGIS webinar. And we're also very grateful for the support of this research from the GISPS, the Japan Society for the Promotion of Science. And this research was done about 2 years ago, which recalls me of the wonderful experience working with my colleagues at Tokyo Tech. So this is the structure about this webinar. As May already introduced quite a lot, I will skip this part. And the outline of this presentation includes 5 main aspects. First of all, I will introduce a heterogeneity of urban dynamics and supported by the complex network or organized complexity perspective, leading to the topology of the hotspots derived from the tweet-based trajectories. Then I will introduce how we think, how we design the urban simulation model based on the hotspots and the street network. Then we conduct 2 case studies in London and Tokyo, 2 metropolitan areas, to explore the large-scale urban movements and urban structure. Finally, summarize the work. As we know that cities work as complex systems because they show a great nonlinearity of city structure and heterogeneous dynamics. So it's better for us to view the city from the perspective of organized complexity proposed by Jacobs back to 60 years ago. You should think of in a city, everything is connected to everything else in a complex way. Particularly, those ways cannot be easily handled by formulas or statistics. And in this, only the close observation and reasoning from the bottom up will do. So in this connection, the location-based social media can work as very good proxies because the way how it gathered, how the data is collected is totally based on the individual and a bottom-up approach. So in addition, we also can adopt some complexity science methods, including the network theory, complex network, scaling stats, long-tail distribution, and agent-based simulation, etc., to effectively handle the urban issues. Speaking of this study, which we will investigate heterogeneous urban movements. By means of heterogeneity, we use 3 interchangeable words in this paper. heterogeneity, scaling, and power law. And all these three words refer to a pattern that in a city, there are always a great many small things, a few large things, very few large things, and some medium things. And the ratio of those small, large, and medium things in total constitute a power law distribution. So we can take an example of the user trajectories extracted from geo-tagged tweets. If we do a power law test, we in terms of the number of tweets for each trajectory or the length of the trajectory, they're all quite follow the power law distribution. If we take a look on the figure to the left, we can see the tweets spatial distribution and with various densities. Those various density leading to the different type of concentration. And the concentration area in this study we term as the hotspot. Here is an illustration of how the hotspot was derived. Given a number of points, if we do the spatial clustering, and we have the hotspot drawn by the portrait by the right boundaries. And if we get the centroid of those hotspots, we get an illustration for how we can construct the network between them. For the network construction, we can use the user trajectory again to convert the location-based trajectory to the hotspot-based one. For example, if we use one single user's trajectory, we can find a hotspot-based trajectory like this. And if we include all the users, it will automatically become a network. So this is also how the hotspot network was done in this research. And also we model the movement of different users from one hotspot to another, and by assuming that people's movements are always restricted within a street network, we can model the movement from hotspot A to B like the shortest path along the segments. And by doing so, we also count how many times each user passed by a segment. So in the end, the number of the counts will become the movement flow. So this two-layered can also help us to build up the simulation model. So in sum, we have a two-level agent-based simulation strategy. The first level is the random walk between the hotspots. As we can see, the random walk can allow an agent jump from one hotspot to its connected hotspot, or we can introduce some randomness to let the agent jump from one hotspot to unconnected hotspot. So in this case, we can compare different scenarios for simulation. And also we include a number of agents to make the simulation more comprehensive. Regarding the street movement, we adopt the three routing choices along the street. First, we call it metric, which means that the agent go from A to B only consider the shortest distance, no matter how many turns it will have. The second route choice would be angular, meaning that they always take the least angles. And in reality, we think that people may take the mixed choice of two, so between the angular and metric. So in total, this research make use of three routing choices along the street for the movement simulation. So after illustrate the methodology of the study, we move forward on how the case study was done. So the first case study was in London, and we use 100,000 tweets, and which was collected during 1 week back to 2014. And if we take a look on a hotspot, we can see a clear heterogeneous or scaling pattern that there's one very large patch in the downtown surrounding by some medium-sized patch, and those small patches were scattered around the city. And if we connect those hotspots using the user trajectory, we can see how heterogeneous the network is. Actually, it is a scale-free network. So if we do some statistical analysis, especially the parallel analysis, we can find quite a similarity between the two, between the number of the tweets inside a hotspot and the network degree regarding the hotspot. And the parallel exponent are quite similar, and also as well as their R-square value, showing their correlation also very well. This indicates that this abstract, the network between the abstract network between the hotspots can grasp the essence of the human movement at the aggregate level. So the second case study was in Tokyo, and this time we got 30,000 more tweets, and also covering a very big event. The major earthquake happened about 10 years ago. Because we have very good time granularity, we can split up the tweets into two parts. One part is 1 week before the earthquake and 1 week right after the earthquake. And if we check on the number, 70,000 versus 60,000, we can see the human activity indeed was affected by the earthquake. And this result also shown in the hotspot. By looking at the hotspot, we can see before the earthquake, the downtown, the largest patch, is very continuous in the downtown. However, after the earthquake, we can see the largest patch broken into pieces. And also, if we take a look from the network perspective, not only the size was decreased, but also the movement flow, the strength also decreased too. So we can conjecture that the human activity was quite disrupted. And this point also, Professor Saraki will give a more detailed version on that. And then we conduct the simulation, and in the simulation will help us to address two questions. The first question is, do different moving behavior affect the scaling of the flow distribution? So before answering the question, we first take a look on the video. This is the London case, and we can see that movement move back and forth between the hotspots, and then we can find a clear pattern that the minority of segments or minority of streets account for the majority of the flows. So if we turn to the Tokyo case, we can check the comparison between before and after the earthquake, where we can find also a clear difference that before the earthquake, the people movement quite continuous along the major roads. Well, because of the earthquake disruption, the people may have to walk in a short distance. They only can perform a short travel. So we can see how from the overall pattern we can see how much it's being influenced. But anyway, although we have the difference, the flow difference from city to city, from one event to another, this doesn't affect too much on the power law behind. If we take a look on the table, the observed flow between three cases, they're quite similar to each other, around 2.9 something. If we dig deeper and to find how simulated flow looks like, we can see that the combined approach, the simulated flow using the combined strategy, is the closest to the one of the observed flow. So it also confirmed our previous conjecture that the combined distance was the closest in the reality. Then so in summary, we can answer the question like the different moving behavior doesn't quite influence much about the power law nature of flow distribution. The next question is how urban hotspots influence the human movements. So in this case, as I mentioned a couple of minutes ago, I mentioned the randomness introduced in the random walk. So in this case, we introduced the JF, jumping factor, which is, I will not go into much detail, which is a very important parameter calculating the PageRank value. So by adjusting the jumping factor from 0 to 1, which means that the human movement will progressively controlled by the hotspot network. If we check on the plots above, and either before the earthquake or after the earthquake, the parallel exponents of the human movements gradually closer and closer to the observed flow, which means that the hotspot structure really have a impact on human movements in this regard. So as a summary of this paper, first point I would like to make is the topology, where the complex modeling behind the urban hotspots can help us to perceive the scaling structure of both urban forms and human activities. And the similar parallel statistics between observed and simulated movement flow suggests that the routing choices, or I can say the cognitive effects, how people perceive the street environment, have a great impact on the individual pattern maybe, but less so on the heterogeneity of the collective movements. So in the end, to conclude my presentation, I would like to paraphrase a famous quote by Winston Churchill: we shape our city, thereafter the city shapes our movement. I think my part is over. I would like to hand it over to Professor Saraki.
Thank you for the introduction. It's a good opportunity for me to present my study. So the topic of my presentation is the human behavior at the time of the Great East Japan earthquake. Twitter data can help us with the congestion status. So the common point between Dean's presentation and mine is to use Twitter data. So this is the content of my presentation. Mainly, I focus on the third one, the congestion situation on the day and the day after the Great East Japan earthquake based on tweets. And this slide shows tweets before and after the Great East Japan earthquake. And we analyze human movements using a total of more than 100,000 geo-tagged tweets, as Dean said. The number of tweets drastically increased immediately after the earthquake as people posted tweets about the earthquake. And the number remained large for roughly an hour before tsunami struck, then gradually decreased. And this slide is already shown by Dean, but I will mention the detail. So this is already mentioned by Dean. So human activities became more discontinuous following the event. And also the spatial continuity of human movements broke into several pieces in the downtown, like Shibuya, Roppongi, and Tokyo Station. And these changes were mainly due to the temporary shutdown of rest facilities and transportation. It means that subways and railway lines, as well as limited time that shops were opening, etc. And many of tweets sent after the evening related to congestion in the cities, like this. So this photo was taken just after the earthquake. This photo was taken around Shinjuku Station, and this photo was taken near Shinagawa Station. As you can see, these are very dangerous situations. And to understand the situation of congestion, we can use the tweets about congestion with geotag. And this figure compare the spatial distribution of tweets in 2 weeks and just after the earthquake. And this map shows the kernel density map of tweets about congestion with geotag 12 hours just after the earthquake and 12 hours later. And this map shows the spatial distribution of tweets about congestion with geotag after 12 hours later and 24 hours later. And a main topic of my presentation is human behavior, especially congestion by the crowd. And I want to know when, where, and how much was local and sudden congestion by the crowd occurring. And the difficult point is that the percentage of geotag tweets is very limited, only about 0.2% of the whole tweets. And my approach is that to estimate the degree of crowd congestion in each facility or on each street in real time based on information posted to SNS, which are excellent in immediacy and openness. And first, when. So this is a graph shows the time transition of tweets about congestion. So as you can see, the total number of tweets rapidly increase more than 5 times immediately after the occurrence of the main shock, and then gradually decreased. On the other hand, the number of tweets about congestion indicated by the other lines was particularly large after 6 p.m. on 11th and after 8 a.m. on 12th. And next, where? So you can see the spatial distribution of number of tweets about congestion. As I mentioned before, the percentage of geotag tweets is quite small. So we utilized proper nouns and place names extracted from tweets about congestion. Among subways and railway lines, there are many tweets about congestion related to the subways and the Yamanote line. And among railway stations, the number of tweets about congestion is large at the major railway terminals like Shibuya Station and Shinjuku Station, and so on. And next, when and where. So the number of tweets about Ginza line, please look at this graph. And the number of tweets about Ginza line drastically increased after 8 p.m., but since then it gradually decreased. Therefore, we can guess that congestion on the Ginza line was temporary. On the other hand, in Shinjuku and Shibuya and Yokohama, the number of tweets about congestion gradually increased like this and to the next day. Therefore, we can guess the congestion state lasted for a long time. And the timing when the number of tweets about congestion increased correspond well with the operation resumption time of railway lines. This result suggests the usefulness of such tweets for quick grasp of congestion. And finally, I want to explain ongoing and future works. I mean, how much. So this graph shows the estimation of congestion degree based on specific words in tweets. In this graph, 52 expressions are sorted in descending order of average evaluation point answered by about 1,1200 respondents. And the second one is to estimate congestion degree based on photos in tweets. And this photo in this slide, 100 photos are sorted in a descending order of the average congestion level based on the answer of 1,200 responders as well. And I believe the image recognition approach using deep learning will also be useful. It means that supervised learning based on annotation. And this is the last slide of my presentation. Thank you for your attention.
Well, thank you, Professor Oki. Next, Professor Osaraki.
Yeah, it's my great pleasure to have this opportunity. Thank you very much. Let me briefly introduce myself. I'm Toshio Saraki from Tokyo Institute of Technology. These are my research topics. As you can see, my interest is so varied. However, recently I'm focusing on the spatial-temporal analysis of human movement for disaster mitigation planning using simulation technologies. The first author, Dr. Madin, had been studying in my laboratory as a research scholar, supported by JSPS for 7 months. Part of this research was conducting his stay in Tokyo. Therefore, part of this research includes 2 aspects, human movement and disaster. So regarding the case study of Tokyo, we analyzed urban structure from a new perspectives, comparing the human movement before and after a major earthquake. So in my talk, let me very quickly give you additional information on what the human movement before and after the event was. So East Japan earthquake occurred on Friday afternoon, 2011. As you may know, the human casualty was mainly caused by big tsunami, followed by major earthquake. Although there was no physical damages in Tokyo metropolitan area, every railroad was paralyzed and widely confused. Over 3 million people could not return home on that day. And people who couldn't contact their family members and felt uneasy began to walk home at once. The main roads were very crowded and seriously congested by cars. And also the activities of emergency vehicles were also obstructed like this. So I'd like to show a movie that visualizes human movement before and after the event, captured by GPS instead of Twitter. Okay, and before that, I'll show you the spatial range to be displayed from now on. So here is a link railway that forms a core of Tokyo. Please refer to the size of this ringley. Okay, let's have a look at the human movement on that day. Okay, and the time is shown here. It represents the movement of people at a normal time before the earthquake. You can see the urban structure from the people moving at high speed. I'd like to draw your attention here that 4-layer network determine the human movement: railways, highways, and the general roads in the pedestrian spaces. The great earthquake will occur soon. It's 2 o'clock now, and then, yes, now, okay? You can see that the number of moving people has dropped rapidly, and its speed has become extremely slow. As I mentioned previously, public transportation was paralyzed and main roads were seriously congested by cars. Therefore, mainly only the pedestrian movements were visualized here. In this sense, the human movement after the event were determined by single-layer network available for pedestrians, totally different from the before the event. So as the time goes by, the number of people moving by cars at high speed increases. However, the railway was not completely restored the next day, and the usage of railway was limited. Okay. This is the result of agent-based simulation, which describes the human movements after the event. Due to the limitation of time, I can't explain the details of the simulation model, and the black dot indicates walkers, but displayed 1 from 10 people for simplicity. And the red dot indicates the level of crowding at temporary shelters, and blues are support stations, and the greens are number of temporary stayers at the train stations. Okay, these are hotspots of formed by crowds, as you can see. Hotspots never static at all and changing very dynamically. That means it will be possible to analyze urban structure from not only static viewpoint, but also dynamic perspective by using this kind of human movement data. So, a brief conclusion. A lot of research have been carried out on structure of urban spaces. Due to the limitation of available data, they have been conducted mainly from the static viewpoint. The various kinds of location data which describe the urban scale human movement in our daily life are available these days. So I believe that the high detail spatio-temporal human movement data can be of great value in new research on dynamic urban structures. That's all. Thank you for listening.
Well, thank you, Dr. Saraki. Dr. John?
Okay, thank you. Welcome to this presentation. And you can see the title that I'm going to present is a new kind of city science built on living structure. It links to human mobility or human activity in general, and it helps to answer why human mobility or activity, including COVID-19, can be well predicted through the underlying living structure. It is a new kind of science because city science goes beyond science as currently conceived, mainly about understanding how things are rather than creating or design things. In other words, the new kind of city science is not only about how cities are, but also, more importantly, about what cities ought to be. So living structure is a mathematical structure that it existing pervasively in our physical space, just as air. We cannot see it, but it is everywhere. Living structure can be well reflected in human mind and heart, triggering a sense of liveliness or vibrance. I will begin with 3 fundamental issues about cities: how they look, how they work, and what they ought to be. I will use one example to illustrate living structure, which is defined under the third view of space. Space is neither lifeless nor neutral, but a living structure capable of being more living or less living. I will present 2 fundamental laws of living structure and 2 design principles for making living or more living structures. Next, I will look at in detail the science of living structure, which is built on the new theory of centers, supported by the discovery of the 15 properties. These properties can be well reflected in human mind and heart, triggering a sense of the liveliness or sense of the beauty. This sense of the beauty can be well captured by the so-called mirror of the self experiment, using human beings as the measuring instrument. The science of living structure is a new kind of science for which I will present a research agenda briefly in the end. So there are 3 fundamental issues about a city: how they look, how they work, and what they ought to be. These are also 3 fundamental issues of geography, as the science of the Earth's surface. Conventionally, geography concentrates largely on the description of the structure, literally meaning the description of the Earth's surface. I argued, and I will argue again, that without understanding how it works, the underlying mechanism of dynamics, we cannot well describe the Earth's surface. Cities or geographical space in general are complex or non-linear systems, so they cannot be well described by Euclidean and Cartesian geometries. More importantly, structure or morphology is the outcome of the dynamics. So the second issue is larger than the first one, or the second issue contains the first one. The third issue is about how to make cities to be living or more living. And it is even larger, being the largest among the three. The science of the living structure goes beyond physics towards a design science. The notion of the design or design science, therefore, has the largest scope, larger than physics or larger than understanding how things are. The notion of the design implies that the goodness of design can be measured or quantified. It is a matter of the fact rather than opinion or personal preferences and conventionally conceived. To further clarify this point, let's use a parable. Before the invention of thermometer, warmness was a kind of a human feeling. Yet, after the invention of thermometer, a warmness became the physical concept of temperature. Nowadays, how good a city is still considered to be opinion or human feeling. But in the near future, it may become a quantifiable fact. Living structure is to livingness, is what temperature is to warmness. So let's now use this painting, namely Composition by the Dutch painter Pieter Mondriaan, one of the most famous 20th century artists who is well known for using some simple geometric shapes and the primary colors of red, yellow, and blue. Conventionally, we see this painting consisting of 7 pieces, among which the most salient pieces are in red, yellow, and blue. However, instead of this static view, or sometimes we call the Lego-like assembly view, we can see this painting consisting of the 18 recursively defined substructures as shown in the panels B, C, D, and E. In total, 18 substructures. In other words, this painting is evolved dynamically from empty square in a step-by-step fashion. From panels B to C, we see there are far more newborn or newly generated substructures than other ones. From C to D, there are also far more newborns than older ones. So the notion of the far more newborns than older ones recurs twice. So it is the living structure. In addition, we can notice that at each iteration, except the first, the far more small and largest. Having seen this example, it is not difficult to figure out what is the living structure. It is such structure in which there are far more small substructures than larger ones. Note that the notion of the far more small and largest must be recurring across all scales. On the other hand, small substructures are more similar in size on each of the scales. The notion of the living structure was first defined by Christopher Alexander under the organismic worldview, which first conceived by the British philosopher Alfred Whitehead. The organismic worldview extends the mechanistic worldview to include human beings as a part of the world picture. In other words, we human beings are part of the world rather than separated from the world. Under the organismic worldview, Alexander formulated the certain view of space. Space is neither lifeless no neutral, but a living structure capable of being more living or less living. Under the third view of space, the entire Earth's surface is a living structure, ranging from the largest scale of the Earth's surface to the smallest, a tiny ornament of centimeters, for example. Living structure is said to be governed by two fundamental laws, scaling law and turbulence law. This is a recurring notion of the far more small and largest for the larger substructures, yet more is similar for the small substructures. These two notions, far more small and largest, and more is similar, underline the two fundamental laws of living structure. To generate living structure, there are two design principles, namely differentiation and adaptation. The differentiation means that large substructures are differentiated or partitioned or decomposed, like cell division into small ones in a step-by-step fashion, while the adaptation principle means to ensure that the generated substructures are well adapted to each other, that is, to meet the two fundamental laws. The science of living structure is a new kind of science under the organismic worldview rather than under the currently conceived mechanistic worldview. It is built on the theory of centers, supported by the discovery of the 15 properties. Living structure is such a physical structure that can be defined mathematically. In other words, the degree of liveliness or the degree of the beauty can be computed. Importantly, the degree of the beauty can be reflected in human mind and heart, for which a new observation method was developed, the so-called mirror of the self experiment, that is using human beings to measure the degree of liveliness according to their own feeling, somehow like ask people to tell the temperature, how much degree the temperature, instead of using thermometer. Emerging geospatial big data such as nighttime imagery, open speed map data, and location-based social media data provide the powerful means to do the science of living structure. With emerging big data, cities or city boundary can be delineated using the global scale data like tweets. The notion of the nature cities is defined from the bottom up using open access big data, so it is a universal definition. It can be traced along the time dimension to examine how cities are evolved. This slide shows the evolution of nature cities month by month using the location-based social media data of Bright Kite, with cities of Chicago and New York as two examples. The discovery of the 15 properties is the foundation of the theory of centers. These 15 properties are pervasively occurring or recurring in nature, as well as in what we human beings build and make, including, for example, buildings, cities, and artifacts. We don't have time to get into the detail of the 15 properties. However, there are a few points to make. First, these 15 properties capture very well how things look geometrically on the surface. And in the meantime, they act as transformation properties for design sense. Second, the 15 properties were distilled by Alexander from his classical work of pattern language, the 253 patterns. Third, the 15 properties have been further distilled into two laws and two design principles. In other words, the two laws and two design principles came from these 15 properties. We have seen previously the painting A composition meets the minimal condition of being a living structure, for the notion of the far more newborns than older ones recurs twice. Here is another painting, painting B, is more structurally living or more structurally beautiful, for the notion of the far more newborns than older ones recurs 3 times. It is the difference of the twice and 3 times that makes painting be more living or more structurally beautiful. In other words, the degree of beauty or degree of liveliness can be accurately computed. The computed degree of beauty or structural beauty, so to speak, can be well reflected in human mind and heart. It is essentially the underlying living structure that tricks a sense of the beauty or liveliness. The more substructures, the more beautiful. The high hierarchy of the substructures, the more beautiful. Alexander developed the mirror of self experiment. 2 images or 2 things put in parallel side by side, and the human subject is asked to pick one. He and she has a better sense of the feeling or belonging. Taking these 2 paintings, for example, if they are painted in 2 t-shirts, which one you would love to have? It was found that most people would love to take the right one. Note that the mirror of self-experiment is not just a simple perception test, like, dislike, or the so-called inter-subjective agreement, but to examine the existence of living structure. In other words, it is the underlying living structure or the notion of the far more small than largest that tricks the sense of the beauty or sense of the liveliness. Now let's compare these 2 city plans. To the left of the screen, it is a city plan for the city of London, and the 6 colored panels show its hierarchical levels. From this, we can see how it was transformed to become more and more living. To the right of the screen, it is a part of the Manhattan city plan, and the 3 colored panels show its 3 hierarchical levels. In comparison of these 2 city plans, there's little doubt that the city of London to the left is more living or more structurally beautiful. To this point, I hope I have made it clear that the living structure or the third view of space is really powerful, not only for better understanding city structures and dynamics, but also for effectively transforming cities and communities towards a sustainable society. The city science is a new kind of science, a new kind of the design science, for which I'll present briefly a research agenda here. The first, the emerging geospatial big data, in particular location-based social media data, provide a powerful means for revealing living structure and its dynamics, and to understand how human mobility or human activity shapes and is shaped by the underlying living structure. Second, the structured beauty has emerged as a new concept for image understanding and computer vision. It can help measure or quantify the liveliness of space. Third, living structure or structured beauty in particular can help assess goodness of open design, that is using 2 design principles and the 15 properties to guide open design and planning. In other words, open design or planning is no longer based on expert opinion or personal preferences, but based on the beauty to assess the goodness of open planning. It would help transform modern cities to be living or more living. The fourth, along the middle of self-experiment, neuroscientific evidence can be gathered using, for example, eye tracking, fixation points, and other biometric data. This data will prove how living structure is reflected in human mind and heart, and further verify how this kind of reflection varies from people to people in terms of their culture, gender, and races. Okay, it's time to draw a conclusion of this presentation. Let me highlight some few points. City science built on the living structure is a new kind of science, or a new kind of design science, because the goodness of design can be measured or quantified. The three fundamental issues about the city: how it looks, how it works, and what it ought to be. Scaling law and turbulence law are the two fundamental laws of living structure. The two design principles and the 15 properties can help transform cities to be living or more living. There are more works to be done in the future and to transform cities from conventional science to the new kind of design science. Thank you very much for your attention, and questions and comments are very welcome.
Well, thank you, Dr. John, and it's great to have a series of presentations from very empirical to simulation and eventually provide the conceptual framework. So now we open the floor for questions. I know that we only have 1 minute left, but since we come starting a little bit late, so we would like to entertain as many questions as possible. Dr. Gao put a question in the chat. Dr. Gao, are you still here?
Yes. Hi, Dr. Yuan.
Yes, please. Please ask your question.
Yeah. Can you hear me?
Yes, very well.
Okay.
Thank you for waking up early.
Yeah, very interesting presentation. Thank you for the panels. Actually, I'm more interested in the about the content of the IJGIS paper because I read many times because in my topic area, and I noticed that your team used their team-based, their triangulated irregular networks for their hotspot detection, and then analyze the human movements between different hotspots. So my question is because oftentimes we directly model the human movements between points of interest or region of interest. We can just call maybe place of interest. I wonder what was the rationale and to use the team-based detection and then construct the human movements and then do the agent-based modeling. So yeah, this is my question. Thank you.
Marty, you are muted.
Dr. Ma, you are muted.
Yeah. So it's now okay? My voice is clear? Yes.
Very
thank
good.
you. Thank you, Dr. Gao, for your interesting question. I think I can start with the answer, and maybe Professor Jiang can help me to wrap up. The team-based modeling is one very promising method developed by Professor Jiang, actually. Who built up the natural city at the country scale or even global scale for delimit the city boundary, because he thinks that the city is a concentration of human activities at the very wide level, region level or country level. So I borrowed this method into the study at the city level. In this case, if we use the team-based method for doing such analysis, we can get the hotspot. So the hotspot to city relationship very much like the city to country relationship in this regard. So also using team-based approach can help us to model directly the proximity between the points, and also those edges, the length of the edge or the proximity distance can automatically follow a power law or long tail distribution using team-based model. So in this case, we don't need to decide the cutoff. We use the mean value directly for the cutoff distance of the clustering. So in this case, we derive the hotspots based on the proximity between the points. And for the second for your second question, you mentioned the POI, place of interest or point of interest. I do think it is a very promising direction. In this study, we use tweet location, single data source. In the later on, we can of course embed the other data types like you mentioned POI. And then POI, I quickly walk through in my mind, which is we can categorize different type of POI and make different types of hotspots. And again, adopt the trajectory between those hotspots can give us maybe more a comprehensive human movement model inside the urban area. Yeah, that's my quick response to this question, Dr. Sun.
Very good. Dr. John, you have a comment?
Yeah, I just want to supply this discussion. Very interesting. I have 2 points to make to the question raised by Dr. Gao. The first is that this to approach the traditional place hotspots and this team derived, we call the patches or nature cities. Basically, they are very match each other. So we don't think it's, even though we rely on the big data to derive these patches or hotspots, but the derived hotspots pretty much, according to our comparison, pretty much to the what we conventionally identify places or hotspots, whatever you want to call it. And the second point I want to make is not only the team-based, but the many other approaches we have adopted. For example, if you take the image, the individual pixel can be act as the team age or the triangle of the team, because this is really inspired by the wisdom of the cross idea. If there are massive amount of the elements or components of system, and they are very heterogeneous, and then if we could take average of this pixel value or age length or triangles, or even in another study back to 10 years ago, we take the street block automatically derived from the country scale or city scale. So we see that not only the team ages, team triangles, but also image pixels and the street blocks of the massive OpenStreetMap data all can function in the same way. They form a kind of the cross, but because this cross have certain wisdom, wisdom cross, by taking average, it can really differentiate the entire system into 2 parts, the head and the tail. And the head often represents the high density space or high density hotspot. That's the idea came from, So I hope my answer helped to stretch to other similar things like speed blocks and image pixels. Yeah, thank you very much.
Very good. And we have another question from Mr. Jalani. The basic question is, you use the Twitter data to show the congestion, and he thinks that they might have other data useful for urban human behavior. Do you have an opportunity to explore other social media data for the purpose, like Instagram or Lines or WeChat or Facebook?
Yeah. Thank you for the question, Professor Jairani. I will answer your question. So there are some reasons I used Twitter data. One is that the Twitter was a more popular tool in 2012 than Instagram or Line. So there are few opportunity to use such tools for my analysis. So this is one reason. And another reason is the data availability. So to obtain the Twitter data, we just use Twitter API, but it's a bit difficult to obtain the data from Instagram and Line for academic use. So this is the second reason. And also Twitter is now used even by the government and the municipalities in the disaster response situation. So I think even in these days, Twitter data is very useful to grasp the such kind of emergency situation. Thank you for your question.
Yeah, I also agree that Twitter data is just so much easier to use than Facebook, and the intention to make the public announcement of your situation or your ideas is quite different from like a Facebook or Instagram. It's only within your social network. And as a follow-up question, I do think that the idea of using Twitters or other social media data to look at human behavior or a dynamic of human distribution, population distribution is very interesting. I also very think that the compare before and after earthquake is a very powerful research to show how the major disasters influence human movement and how the urban structures constrain the movability of people after the event. But the problem is that, well, we know that we only look at where people report. If a tree fall down, nobody see it, and that will not be reported. So can you comment on the potential biases or some missing observations maybe embedded in your either simulation or data analysis, and how that reflect to what Jiang said, that you have to be more divisions and have a more little things to make things more living. But the missing observation may make the things, little things suppressed in some way. So it's really a question on the empirical analysis perspective, but also in the overall conceptual design of the research. Comment or reactions?
How about Martin?
I do think Professor Jiang can help to address this question, because I also, when I work with Professor Jiang, when we attend a conference, I heard also in the review process, I heard this question maybe twice or I think several times. Yeah, when I address such questions, I also follow Professor Jiang's advice, saying that we don't want to say that we see the ground truth of human activity. We do believe that it is data. It is a tweet data. What we analyze is what the tweet data give us. We only model the data itself. So data will speak for itself. Then we just observer in this scenario. But may raise the question is very important. You mean that we may have a biased version of the phenomenon. So how to handle this kind of problem? I think Professor Jiang may be more helpful in this regard.
You are muted again.
Sorry. Okay. Yeah, this sampling bias initially came from the small data. When data is very small, if we have a population, 10,000 population, when we take, let's say, 100 or 1,000 out of 10,000, then if this bias, of course, sampling bias have effect on the outcome of the analysis. But my argument, and Martin has said earlier, that even though the percentage is very lower, for example, only 0.2% is used, but the larger volume or larger size is significant. It's very big. Yes, sure, there are certain people who failed to report, out of this sample. But I think that the data volume or data size itself is already big enough to illustrate or to review the living structure. So to large extent, even though the percentage is so lower, but the volume is big enough to reflect the fact of the far more small and largest, the scaling effect or the living structure which we wanted to reviewing is really good enough. So it's from this perspective. And also we did really, for example, if we compare the hotspots derived from either from OpenStreetMap data or from tweets, Martin did already many times, we compare to the conventionally defined POI, they're pretty match. Sometimes it's a 90% match. So really, I mean, this sampling issue or sampling bias is the issue for small data analysis, but not issue for big data analysis. This is my argument. Sorry. Yeah.
And any other perspective on this?
So linked to this sampling is also data quality issue. If you look at the literature and many discussion about the data quality, uncertainty, I think my view is the data quality, sampling bias are the issue of the small data, not so much to the big data.
Mm-hmm. Yeah. Okay. Well, with that note, I hope that we will see more publications from this research group, have a very diverse and very interesting research questions, and also have empirical simulation and conceptual research elements. It's really what to say, now we are in Olympic, right? It's the gold medal research team. Very well, and thank you for your presentations. And I think we will, I apologize to run over time, but it's a great talk, and I will do a little bit editing on our videos and then post the videos on the IJGIS YouTube channel, and I will inform you when the video is available. Thank you all the participants coming today. Thank you for our presenters to give us so many interesting ideas to think about today. It's early here in the United States, and I have a whole day to think about your new ideas. All right. Well, thank you. And
thank you so much.
For people in Asia, good night. Hope you will sleep well tonight.
Thank you very much for Professor.
Thank you very much.
Yeah, thank you.
Thank you, Professor.
Thank you.
Take care. Take care.
Take care. Bye-bye.